single zero of any polynomial function. So first and foremost, we need to remember the following fact. The number of roots, i.e. solutions, i.e. answers, not necessarily the x-intercepts. Remember, x-intercepts can have a multiplicity of something. So the number of roots that you get should be the same as the degree, bless you, of the polynomial. So if I have a quartic polynomial, I should have 4 roots. Some of them can be the same, that's fine, but I should have 4 roots. If I have a cubic polynomial, I should be able to identify 3 roots. If I have a quadratic, I should be able to identify 2 of those roots. If it's quintic, then I would have 5 roots. So that degree, how we identify the degree of the polynomial, it's the highest exponent, right? The largest exponent of your polynomial is going to be your degree. All right, so we got that down. So now what we have, looks like a lot, not that complicated. We've got 2 theorems that we need to cover today. The first is the rational root theorem. Well, rational stands for what? What does a rational number look like? Well, we got the word ratio. What does a ratio look like?
Like 1 dot 2.
Yeah, or it can be written as a fraction, right? So 1 over 2. So a rational number is any number that can be written as a fraction. Good. Rational root, so that means any answer or root or solution that is a rational number, any number that can be written as a fraction. So our rational root theorem states the following. If we let p be a polynomial function with integer, and you're only going to be given ones that have integers, so don't worry too much about that. I'm not going to give you fraction coefficients. Integer coefficients in standard form. P over Q kind of got bumped down there. Then the ratio, that's a lowercase p over a lowercase q, written in lowest terms, is a root of our function. Yeah, fix that, that's bothering me. Shift it down a little bit. There we go. All right, so it's a root of the function p of x is equal to 0. Because remember, if you were to evaluate any function and get an output of 0, that would be your x-intercept, which would be the solution, which would be the root. So then the following would have to be true. First up, we would know that p has to be a factor of the constant term. So now if you think about a polynomial in standard form, the constant term is the number that doesn't have any x attached to it, right? So that's our p. The q is going to be a factor of the leading coefficient. So we're looking for the leading coefficient of the polynomial. So let's quickly wrap our brain around the word factor. What are factors of the number 8?
4, 2, 8, 1.
So factors of 8. We've got, how do I want to write this? 1 times 8, right? 2 times 4 would be all factors of 8. What would be factors of 2? Just 1 and 2. Good. What are factors of 20? 1 and 20. 2 and 10, 5 and 4. Oh, I wrote those backwards. 4 and 5 would be all factors. Okay? So when we use the rational root theorem, what's kind of nice about the rational root theorem, again, we're going to cheat and use our calculators, but what's nice about the rational root theorem is I can use it to find all the possible zeros that could be solutions to my polynomial function. Not saying that every single one will be a solution, but the list will be the possible solutions. So let's see what this looks like. Is everybody good? Okay, so here's our first polynomial. We got f of x equals 6x to the fourth plus 7x to the third minus 12x squared minus 3x plus 2. So what we're looking for to list all the possible rational roots would be all the factors that make the form P over Q, where P is your constant, Q is your leading coefficient. Then we're going to do factors of them. So what is my constant term here in that polynomial? It is 2. Does everybody see why 2 is the constant? Doesn't have an x attached to it. So if 2 is my constant term, what are all factors of 2? 2 and 1, so I'm going to put 1 and 2. What's my leading coefficient? So go to your highest degreed monomial, and then what's the coefficient there? 6. Good. What are factors of 6? 1 and 6, 3 and 2. Good. So we made our list of our factors of our constant. We made list of our factors of our leading coefficient. Everybody good so far? You don't have to. I just like to. So those are the only two numbers that I'm really concerned about. And then it's remembering that it's going to be constant factors over leading coefficient factors. So now we're going to make as many combinations of rational numbers using these factors. You ready? So I'm going to start here with this 1. I'm going to put this 1 over that factor that is a 1. What does 1 over 1 simplify to? 1. Good. And then because I can have both options, I need to put a plus and a minus there. So one of my possible x-intercepts, one of my possible roots, one of my possible solutions could be positive 1 or negative 1. I don't know, but it's a possibility. Now let's make another rational number. Let's put that 1 over 2. Oh, is that already simplified? Yep, so I'm going to put plus minus 1/2. Now I'm going to put that 1 and put it over 3, which is already simplified. So I'm going to say plus minus 1/3. What's the last combination with 1 in the numerator? Plus or minus 1 over 6. Has everybody got that?
I got it right there.
Okay, so now we use that factor. Let's jump over to the other factors. Now I'm going to make all combinations with 2 in the numerator. I'm not going to rewrite duplicates. 2 over 1. Do I have that written yet? Nope. So 2 over 1 would be just 2 plus minus. Do you guys need me to keep going with that top line, or we go with the bottom line?
Oh, I thought you had to do it.
No, I was just showing how. So 2 over 1. 2 over 2 would be what?
1.
Do we already have 1? Yeah. 2 over 3 we don't have, so let's list that. So plus minus 2/3. And then our last one is 2 over 6, which is 1/3. Do we already have 1/3?
Yeah.
Yes. So this would be your possible list of the zeros. Okay. Now think about synthetic division. If I picked randomly one of these numbers, which one would you pick randomly?
1 and 2.
You pick 1 and 2. All right, don't put this in your notes, just watch. Can I erase this? Okay, so let's say we chose, let's go with 1 first. And if I did my synthetic division, so 6, 7, negative 12, negative 3, 2. And do my synthetic division, so bring down the 6. 1 times 6 is 6. 6 plus 7 is 13. Multiplying gets you 13. Adding is 1. 1 times 1 is 1. Negative 2. Whoa, we picked very well. How do I know that 1 has to be a 0? Because my remainder ended up being 0, right? That was a pretty good guess. Usually doesn't happen that well on the first try. Pick another one. What was another number from our list? You want to go 2? So if I do the same thing with 2, 6, 7, negative 12, negative 3, 2. So we have 6, 12, 19. This is going to get ugly. What is that? 38. 38 minus 12 is 26. We see how this is not going to end well. 54, 51, 102. Is that going to get me a remainder of 0? No. So is 2 a solution to this? No, it's not. Okay. But lucky for us, we did get to our solution right away. But since I started with a quartic, this now ends up going to a degree of what? 3 to a cubic. So that means I'm going to have to do how many more synthetic divisions to take it to a quadratic? 1 more. So you're going to need to do 2. So how many options do we have? We had 1, 2, 3, 4, 5, 6 times 2, so 12. So we could ultimately do 12 different synthetic divisions on a piece of paper and try to find which one gets a remainder of 0. Does that sound like a lot of fun? Yeah. Okay, Ben's going to go for it. Or we could cheat, get the graphing calculator out, go ahead and do that, graph it, and give me 2 actual solutions.
So you just pick from the list after you graph?
Well, the list just lets you know these are your possibilities. Technically, if we were in a world without technology, we would have to keep doing synthetic division until we got 2 of them to actually work out.
Oh. So we don't even have to do that list, really?
Well, you need to be able to know, the rational root theorem is a pretty important concept, so you need to know that these are my possibilities and this is where they're coming from.
1 is at 0.
So we have 1 at 0, and what else? We already got 1. We know we have 1, right?
And negative 2.
1, negative 2.
Negative 1/2.
You want to go with half?
No, I mean like on this thing. Yes.
Oh, okay. Let's pick some. Let's see if there's nice ones.
Negative 3.
Negative 2? All right, we already did 1. Okay, so let's go ahead and do the synthetic division with 1. And then we're going to do synthetic division with negative 2. Does everybody see negative 2 as a x-intercept? Yeah. Okay, so let's do it. So actually put this in your notes because this is what you're going to have to do. So for part B, find all the roots. So 6, 7, negative 12, negative 3, 2. Work through that, bring down the 6. It's always your first step. 1 times 6 is 6. 7 plus 6 is 13. 1 times 13 is 13. Adding makes 1. 1 times 1 is 1. Adding makes negative 2. Negative 2 times 1 is negative 2, so now we get 0. Don't even put your x's in. Because I know I had a quartic, I need to do 2 synthetic divisions. So now let's do it one more time. So bring down that 6.
Oh, wow.
6 times negative 2 is negative 12. Adding makes 1. Negative 2 times 1 is negative 2. Adding makes negative 1. Negative 2 times negative 2 is positive 2. That gets you to 0. You don't need to do that 0 because that was your remainder, so really that's not there anymore. So So because I got remainders of 0 for both of them, I know for sure that these were true zeros. So there's 2 of them. What does that look like as a quadratic? 6x squared plus x minus 1 is equal to 0. Can we factor that? We ask ourselves.
Yes.
So 6 times negative 1 is negative 6. Factors of negative 6 that get you to positive 3 would be positive 3, negative 2. Don't forget your leading coefficient is 6. Some of you guys forgot to do that on your 7-4 quiz. Reduce those fractions. So we get 1/2, negative 1/3. What do those look like in factored form?
3x minus 1.
Yep.
2x plus 1.
3x minus 1. 2x plus 1. For fun, let's put it all the way through factored form. Because I had a degree of 4, I should have 4 linear factors. So what would these look like as linear factors?
X plus 2 and x
Yeah.
minus
If my
1.
0 is negative 2, think backwards. The linear factor would have to be x plus 2. And if I have a 0 of 1, the linear factor would be x minus 1. So this would be your answer totally in factored form. Isn't that lovely? There it is. We factored it. So there it's in factored form. So what are all your rational zeros? What are my 4 solutions?
Negative 2.
Yeah, so negative 2, 1/3, negative 1/2, and the last one is 1.
Wait, why is that negative 1?
Which one?
Oh, because it's positive, okay.
Yep.
1/3 is outside.
Wait, do you get to negative 2 and the 1 from
Those came from our graph.
okay.
Yes. Okay. So find all your rational zeros. There they are. Were they on our original list? Yeah,
Yes.
they were. Okay. Rational root theorem. See how that works?
Do you have to do that every time?
Nope. Well, I'll do this section. There's more. Huh?
Do we really need to do the P over Q if we can just do that?
You're going to be asked to list all possible rational zeros, yes. All right, can we do another one? I'm going to skip a few.
I think we just learned how to do it.
Let's go to this one. F of x equals x to the third plus x squared minus x plus 2.
Do you have this class tomorrow?
We have this class tomorrow, yes.
I have no time to do any homework. Okay. You lose.
Let's quickly make a quick list. What's my constant? 2. Factors of 2 are 1 and 2. What's my leading coefficient? 1. Factors of 1 are 1 and 1, just 1, right? So this is going to be a really small list. So what are my possible rational zeros? Possible zeros, plus or minus 1, plus or minus 2.
So we can have to graph that.
Well, I mean, if you want it to gamble, we know that there has to be 3 of them. There's 4 of them, so you could just pick one if you wanted to go for it. Which one do we want to go with?
Positive 1.
You want to go with 1? Are we sure it's 1?
It's negative 1.
I'm going to graph it really quickly. X to the third plus x squared minus x plus 2. Graph.
Ooh, it's not.
Ooh, I only see one x-intercept on my graph.
It's a multiplicity of 4.
What's it at?
Negative 2.
Negative 2, all right. But I have a degree of 3, so really how many synthetic divisions do I need to do?
Yeah.
I only need to do 1 to take it to a quadratic, and then we'll see what's happening. Okay, so either at negative 2, there's a multiplicity of 3, oops, or something else is happening. So let's put that negative 2 in our half box. Coefficients are 1, 1, negative 1, 2. Work through that synthetic division. Bring down the 1. Negative 2 times 1 is negative 2. Adding makes negative 1. Negative 2 times negative 1 is 2. Adding makes 1. Multiplying gets negative 2. Remainder is 0. What's the resulting quadratic?
X minus X.
Good. X squared minus X plus 1 equals 0. Is that factorable? Are there any factors of 1 that get you to negative 1? Nope. Okay, well, it's a good thing we got some other methods. We could either complete the square. Why would completing the square be a little bit ugly? What's my b value? Negative 1. So that means I'd have to take b over 2, which would get me to negative 1/2. Then I'm dealing with fractions. Or we can go to good old faithful quadratic formula. Let's do that. Here we go. X equals negative b. So 1 plus or minus radical b squared. 1 minus 4 times 1 times 1. All over 2a. What's my 2a? 2. Good. All right. Well, what are we getting underneath there? What's that discriminant?
1 minus 4.
1 minus 4 is,
Negative 3.
oh, a negative 3? Oh boy. 1 plus or minus the square root of negative 3 over 2. What does that turn into?
An
I root
3.
3. I'm going to work up because I'm running out of space. So now we have 1/2 plus or minus I root 3 1/2. That's what this is turning into. How many zeros do we need to have for our answer? 3. We had 1 in our half box. How many are here? 2 because of the plus minus, right? Does that make 3? It just so happens 2 of them are complex solutions, meaning that they have imaginary, which makes sense that our graph only had 1 x-intercept because the other 2 are imaginary. They're not really there.
Well, we have problems like this.
Yeah.
Just with the eye and everything.
Oh, yeah. So your zeros, let's write out our answer. So my x is equal to negative 2. It's our one real solution. I have 1/2 minus I root 3 over 2. Mouse is in the way. And I have 1/2 plus I root 3 over 2 are your 3 solutions. Okay. So this gets us to the last theorem we have to cover today, which is called the fundamental theorem of algebra, which pretty much tells us anytime you end up with a complex solution, you're going to have both the positive and the negative of it. Do we remember what that's called? See, it starts with a C, C-O-N-J-U, conjugate. Remember that word? Okay. So that means that any complex solution and its conjugate will always be a solution of something. All right, so let's write this down. Fundamental theorem of algebra. We're almost there. So your fundamental theorem of algebra states the following. Every polynomial function of degree n greater than or equal to 1 has at least one complex 0. Okay? So, given a polynomial like we did in those last 2 examples, use your calculator to come up with what number you're going to put into your half box. You need to think in your head, my starting degree is 4, so that means I need 2 half boxes. I need to do 2 synthetic divisions to take it to a quadratic. Once I get it to a quadratic, ask yourself, can I factor it? If you can, try to factor it and then get your zeros from that. If you can't factor it, use the quadratic formula and see what the solution comes up. You might get a complex solution that has an I in it, and that's okay. You can have complex solutions. All right? So now what we're going to do is we're going to work backwards using the fundamental theorem of algebra. We were given a polynomial. We took it to the solutions. Now can we take it from the solutions back to the polynomial? It's the last thing we have to cover. Are you ready for this? Sure you are. Huh? So we have this written down? Do we want to do one first without imaginary?
Yeah.
Okay. I'm going to scroll backwards to that one. All right, so let's do one without the imaginary. Where do I have that one? Right here. All right, so we're going to create a third degree polynomial function. So it's going to be a cubic. They're telling us that P of 0 is equal to 20.
Do we have to put in the header?
No. And they're telling us that the 3 zeros is 1, 2, and 5, which is great. Because if I have a third degree polynomial, how many zeros do I need? 3. And they're giving us those 3. So that's perfect. The crazy part is right here. Let's think about this for a second. This represents the x or the y value. The x. If my x is 0, my output is 20. What specific point on the graph does that represent? Right. Not the x-intercept. That's your y-intercept, right? And in the past, our y-intercepts usually end up being what part of a polynomial function?
The vertex.
Not always the vertex. Think back to your quadratic graphs. Your y-intercept was always what?
Like your
Did someone say C? Right? The C of A, B, and C? Okay, so here they're kind of giving it to us for our polynomial. All right, here we go. Let's do this. Now we got to flip our gears, think backwards. If my 0 is 1, what does that look like as a linear factor? X minus 1. If my 0 is 2, what does that look like as a linear factor? X minus 2. If my 0 is 5, what does that look like? X minus 5. Perfect. All right. I'm going to ignore that P of 0 is equal to 20 for now. Can we multiply that out? Let's do it. First two together. Do not go x times x and say x to the third. Ignore this last one and do 2 together first. So if I multiply the first 2 together first, x times x is x squared. I got a negative x and a negative 2x, which makes negative 3x. Negative 1 times negative 2 is positive 2. Now, let's multiply it by x minus 5. X squared times x is x to the third. X squared times negative 5, negative 5x squared. Negative 3x times x, negative 3x squared, plus 15x. That just sounded like Kleenex in my head. Does that sound like Kleenex to you guys? Take the 2 to everything, so it'd be 2x minus 10. Good. Combine like terms, I like that idea. X to the third minus 8x squared plus 17x minus 10. All right, so that would be the case if the problem didn't specify that that y-intercept needed to be 20.
We times everything by 2.
Well, in this case, that's what's going to happen. If it's not so easy to see, this is what you would do. We would go back to this original part right here. And we need to think about what number do I need to multiply this whole entire polynomial by so that when my x is 0, I get an output of 20? Okay, so this is how we're going to do it. I'm going to make a be that number, so some number a times my polynomial with 0, input it, oops, that's 1, input it for x, so 0 minus 2, running out of space, 0 minus 5, needs to equal, we need to make, ooh, that was not working. Get that to be a bright yellow. 0 minus 5, can you guys see that? Equals 20. Okay, so what's 0 minus 1? Negative 1. So this set of parentheses becomes a negative 1. 0 minus 2 is negative 2. 0 minus 5 is negative 5. What do we get when we multiply those together? Negative 10. So I get negative 10a on the left side. Does everybody see that? Equals 20. So what does a need to equal? Negative 2. What did I need to multiply this constant by to get to 20? Negative 2. So if I have to multiply that by a negative 2, what do I have to do to the rest of it? Right. So our last step would then be to multiply everything by negative 2. 34. So we're doing p. So p of x is equal to negative 2x to the third plus 16x squared minus 34x plus 20. For the most case, you are going to be able to see, like if this said 50, what would I have to multiply everything by? Negative 5. If this said negative 60, then I would multiply everything by 6. Okay? And if you can see that, then this step here is unnecessary. Just make sure you do multiply everything through. Okay? All right, can we do a complex one now? So those are the more, well, they're not too challenging. This is it, last problem. Ready? All right, let's do one for a complex. Do we want to do a third or a fourth degree? Third degree? Okay. So we're going to do a third degree again. My zeros are 1 and 3 plus 4i. And they're giving us p of 0 is equal to 50. So that means I got to get that constant to 50.
How would we put the 3 plus 4i?
Yeah, good question. Good question. Let's get the 1 covered first. What's the 1 going to look like as a factor? X minus 1. Good. Now, don't write this, just watch. It's going to work anyways. What did the fundamental theorem tell us?
It could be both plus and minus.
Right, it's going to have both the conjugate to it. So what's the conjugate of 3 plus 4i? 3 minus 4i. So there's going to be your third 0. Right? Degree of 3 means I need 3 zeros. Yes?
Yeah.
Okay, so now here's the magic of everything. Technically, this is what's happening, but it'll work either way. Don't write this, just watch. My 0 here was 1, so we did x minus 1. If my 0 is 3 plus 4i, technically we should be doing what? We should be doing x minus 3 plus 4i. Well, if I distribute that negative, it would go to x minus 3 minus 4i, right? And if I did the same thing for the conjugate, then technically I'm doing x minus 3 minus 4i, which when I distribute that negative would get me what? X minus 3 plus 4i. So these would be your linear factors right here. So could I just write x minus 3 plus 4i and x minus 3 minus 4i and still get to that?
Yeah.
Yes. And that's what you're going to do. Just know that technically we're distributing a negative, but as long as you get to this part, you're okay. So for your linear factors for the complex numbers, all you're going to do is put x minus, and then write what it is. 3 plus 4i. Now we got to get the conjugate. X minus 3 minus 4i. So there are your 3 factors. To make this look nicer, do the ugly part first. Which 2 factors are the ugliest? The last 2, right? And this is just a whole lot of multiplying. And the beauty of it is all the ugly stuff's going to go away. So let's start here. X times x is going to get us to x squared. X times a negative 3 is negative 3x. X times negative 4i. Yep, it's just negative 4ix. Don't make it any more harder than that. Now let's take the negative 3 to everything. Negative 3 times x is negative 3x plus 9 plus 12i. Good. One more set of distribution. Take that 4i. 4i times x is 4ix. I'm going to put it underneath that 4ix because what's going to happen to that positive? They're going to cancel, which is great. Now take that 4i to the negative 3.
Minus 12.
I'm going to put that underneath this one, minus 12i, because those are going to cancel out. Now what's the last one?
Minus 16.
Now be careful with this. You can just plop it there, that's fine. 4i times 4i is what? Negative 16i squared. Do we remember what I squared is equal to?
Negative 1.
Negative 1. What's negative 1 times negative 16? Yes. Okay, so let's combine all this together. Ugly stuff goes away. Do I have any other x squareds? Nope, so I have an x squared. How many x terms do you have? Well, negative 3 and negative 3 would make negative 6x. 9 and 16 makes 25. Whew, that was a lot of work just for that. Almost there. Multiply that by x minus 1.
X cubed.
Yep. X cubed.
Minus
6x squared plus 25x minus x squared plus 6x minus 25. Combine like terms, put it in standard form. X to the third minus 7x squared plus 31x minus 25. Now let's bring this back into play. I need my constant to be 50. What am I going to multiply everything by? Not 2, negative 2. Good. Multiply by negative 2. Sorry for the people in the back of the room. I'm getting really low. Go up here. So my final answer is P of x is equal to negative 2x to the third plus 14x squared minus 62x plus 50. If you were to graph that on your calculator, the only x-intercept would be occurring at 1. If we did synthetic division with that 1, I would get to a quadratic that I'm sure if I either completed the square or used the quadratic formula, it would get me to 3 plus or minus 4i. Okay? That is that.